The chiller worksheets are where you define the baseline operating characteristics of the chilled water plant. This worksheet is broken into sections starting with the general information at the top. For our example building, we have one chiller that operates at any one time, which we'll call chiller number 1. The values that are shown on this worksheet are example values that are included when the tool generates these worksheets. Each of the items in the yellow cells should be reviewed and modified as needed to suit your project. The tool assumes a one-to-one relationship between the chiller and the cooling tower. Systems with a different number of chillers and cooling towers are not directly supported by the tool, although workarounds are possible which become apparent after using the tool and learning its capabilities. We'll discuss this later in the tutorial. It's a good idea to add supporting documentation, such as the central plant configuration, to either the user documentation section of the input worksheets, shown here over on the right-hand side, or in the doc template worksheet, copied and renamed as needed for graphics, which is this worksheet right here. First, we choose the baseline equipment operating schedule. Let's say that the chilled water plant operates similar to the master building schedule selected on the demand tab, namely Monday through Friday, 6 a.m. to 6 p.m. The chilled water plant is off on Saturdays and Sundays. So let's go ahead and select that here. If we did have weekend operation, we would have to rerun the tool for the weekend schedule because weekends are generally off-peak, use off-peak rates, and the tool assumes the same daily utility schedule for all days of the week. So now we can enter values into the rest of the general information section. Note that the chiller type input is used for determining which DO2 chiller performance curve will be used in the calculation. So in our case it will be electric centrifugal chiller. And let's add some other input values for our project, remembering that the yellow and red fields require inputs and the gray cells do not. Note that the chiller type and rated chiller efficiency are used by the CBOA tool to model the energy usage of the chiller. The chilled water plant tabs do not reference the kW per ton regression entered on the main air handler worksheet, shown here. This regression shown on the screen is for the air handlers only, not for the chilled water plant. And remember that the help menu is accessible from this screen by clicking on the gray box with the question mark in the corner. The help menu includes detailed information on each of the inputs on this worksheet. It's also where you can find the calculation methodology used by the tool, shown under the theory section. Below the general information section, we input information about the chilled water supply temperature control method. The tool can accommodate either fixed control strategies or reset control strategies. Depending on which method is chosen, different input fields will be highlighted. So in our case, for our example project, we will assume that it is fixed at 45 degrees Fahrenheit. Similarly, input information about the condenser water supply temperature control method. The tool can accommodate either fixed or reset control strategies. Depending on which method is chosen, different input fields will be highlighted. So for our example building, we'll assume that it is at a fixed set point of 85 degrees Fahrenheit. The next section down is where you define the chilled water load characteristics of the system. The regression is based on outside air temperature. A previous analysis of trend data enabled us to develop a correlation between outside air temperature and chilled water load. So let's take a look at that. Here's the trend data and the regression that goes through the trend data. Note that we've included this chart in the CBOA tool itself by copying and renaming the doc template tab. This helps reviewers see how the regressions were developed. For more information on regressions, view the regressions tutorial. Note the curve fit of the trend data, which is the black line through the points. We can use this equation to input values into the chilled water load regression section on the chilled water plant input screen of the tool. The outside air temperature range for the chilled water load regression should correspond to the selected climate zone outside air temperature range. This can be seen on the Demand tab. For our example project, the minimum and maximum temperatures are 35 degrees and 95 degrees respectively. However, our trend data only spans from 48 degrees to 66 degrees. Since it's rare that you'll be able to gather trend data spanning the entire range of outside air temperatures, some assumptions will have to be made for the tail ends of the temperature ranges. For our example, we'll assume a linear relationship between outside air temperature and cooling load using the trend data we've gathered, even at outside air temperatures outside of what we've trended. So let's go ahead and add some values for outside air temperature, including the minimum and maximum temperatures. Now we can enter the calculated cooling load at these values, these outside air temperatures. We calculated these values using the regression equation, namely the equation that's shown on this worksheet. Note that the curve updates with each point we entered. Also note that the chilled water load at our peak temperature, 95 degrees, is just below the chiller capacity of 570 degrees, which seems reasonable. Next, let's add some information about the chilled water supply pump. So let's go ahead and add these inputs here. Note that the tool allows for 3 types of pump control. If constant volume with bypass is chosen, the pump will maintain the design flow rate. If constant speed with two-way valves is chosen, the pump will ride the pump curve to maintain the entered delta T. And if variable volume with variable drive is chosen, the flow rate will vary to meet the chiller load. In this case, you would also have to enter the VFD efficiency and the minimum pressure set point highlighted here. So you'd select the control method that's most appropriate for your project and enter information in the red highlighted cells. For systems with multiple pumps, you may need to either combine the power draw of these pumps, or if the pumps operate at different times, such as 2-pump operation at hot outside air temperatures and 1-pump operation at all other outside air temperatures, namely cooler outside air temperatures, you may need to define multiple chilled water plant scenarios on the Equipment tab and look to the bin data summary for the savings. Finally, you need to add information about the condenser water system. The first 3 temperatures here are the design temperatures, not the operating temperatures. Also, the tool assumes constant condenser water flow rate. Under fan control, you can select from 3 common types of fan control: 1-speed, 2-speed, and VFD. And the inputs change depending on which you select. So let's go ahead and enter some inputs for our example project here. The CFM fan off value represents the amount of airflow through the cooling tower due solely to natural convection through the cooling tower, meaning when the fan is off, how much air is flowing through. Finally, as mentioned previously in the tutorial, the CBOA tool does not directly support systems with a different number of chillers and cooling towers, but there are workarounds. For example, users can aggregate multiple chillers and cooling towers into a single chiller cooling tower plant, or enter 2 scenarios as different pieces of equipment in the equipment worksheet. Let's zoom in here. Single chiller and 2 chiller operation. The output data on the bin data summary worksheet can then be used for these multiple system scenarios. For example, if 1 chiller operates below 90 degrees outside air and 2 chillers operate above 90 degrees outside air temperature, then those 2 scenarios could be run, and the output on the bin data summary worksheet could be viewed for the savings results. The bin data summary worksheet is discussed in detail in another tutorial.